Well, there goes my power again. It would be nice to have electricity once in a while. Let's see now. Turn that off. Now I've sorted this thing out. I mean, I didn't think it was possible, but now would you look at that? Cut it out. But I understand. I'm pretty sure I understand what a hash table is and how all that hashing stuff works. And it's trivial. There's nothing to it. And I'll show you in a second. Using my map class as an example. I'm going to call it my map class because it actually differs quite a bit by this point from the original. Now here what I've been doing is, well, I'll get to that. Something like what I was doing before, testing the random range. Alright. Now this you test what does this one do? Okay. Well, this is checking for, oh yeah, no, this is important. But that comes later. Okay, so now I have a map. I have declared a map with a key value as a keyword, and F for the key, and the TS string for the value. Now that's not the best example to start with, is it? We'll start with a simpler example. But I'll come back to that. I did a little testing of the timing and how long it took and so on. Right. Now we'll use that later for timing. So a map can take it takes a key type and a value type, and for simplicity I'm going to let the key type be something that could be a 32-bit value, no more, no less than 32 bits. So that means a pointer value or an int or something like that, or a D word. Well, how about int? And for the that's the index. Now for this side we can choose anything. String is comes up all the time. Let's try something a little bit more exciting. How about I invent a special kind of struct? Okay. My special struct. And my special struct has a list in it of what things can be copied around. I don't know. Rectangles. TS rect. So that's like a region, I guess. A list of rectangles. And something else. I don't want to use TS array because that's there's something wrong with that class, and I'm not sure what. I need to fix it. Well, we could add an integer value in here. I don't know. Identifier. Suppose it has an identifier number. Let's say D word. Oh, I know. We got a tick count here. Let's give it a tick count. Counter. That counter might indicate how long the thing has been alive or something like that. Now everything here can be constructed on their own, so I think we're okay to do that. Alright. And so I should be able to add these sorts of things to my map. So let's suppose that the index, the key value is, let's see, it's a rectangle with an identifier and a counter. What could the integer represent? The index. I don't want it to be a linear thing. Well, some random identifier. How about we'll let that be the identifier? So we'll have it like this, and this is the identifier. Something we pull out of the universe. And, we read it out of a file. So the standard way to do that is let's use random range. Oh, no. 100 to 3500. So a great big range. And map of ident equals, we're going to have a struct. We're going to add some rectangles to it and reset its counter. Left, top, right, bottom, a couple more, right, okay, a couple rectangles, and let's reset its counter. And in fact, we don't really need to give this a name. Test. Alright. So that's the syntax. Add an integer number as a key, and well, of course, now how do we retrieve it? I would have to test those other functions I haven't tested yet. Okay, so we'll save this off. How about I'll have an array. Int use, I don't know, up to 100, up to. How about that? Do it all in one line. That will assign the zeroth value with whatever this turns out to be and increment num used. So I could do that again. If I had a constructor for s, I could make it faster. Okay, now what we could do is just modify s and add another one, because it should be copies. How about remove all the rects, and we'll add just 1 second. Something will recognize right bottom. And we'll reset this to counter 2. And we'll just run the same line again. So we're going to have a map for 2 elements. And some identifiers used to retrieve them. So to prove that it works, we could say int use of index num use that. Okay. Now that's an S struct. Rect. Now that pipes into a string. A rect does, and so and a list does. So that'll pipe in. And so will the time. Now an integer value will pipe in. Ticks returns the current number of ticks elapsed without resetting it. Okay, and maybe another carriage return, I don't know. Now this seems quite complicated. This would be very difficult to do, certainly, if you had to do everything manually, keeping track of all these different rectangles and look, the power came on and when it went off. List rect. I know a rectangle. String. Tick. Okay. Which one is it? This is ambiguity. TS list. Well, it's a list of rectangles. I can't tell which one. Operator equal function unavailable in my special struct. Why not? Everything here is copyable. Oh, TS rect. Now, why is that not? Why is that not my standard list? God. Some kind of creepy crawling just tried to crawl up my leg in the dark. No. Oh, non-standard extension. Thank you. Great important information. All right. I guess I've made it too complicated an example. Maybe I'll cut out. Maybe by the time you're seeing this, I might have just jumped right to this point, and if I have, then it's because I went on too long setting this up beforehand. All right. Now, step up to here by selecting that project and pressing the F7 button. Okay, now this is going to construct our thing. I won't go through the constructor yet. Here's our map. It has a few members. Here's my special struct S. Currently doing nothing. I'm adding, now I've added a couple of rects to this list. There are two. Here's one, and here's the other. Okay. Reset the counter. There's not really much to see when the counter resets. Now what I'm going to do is I'm going to add it to the map. First, compute a random number, in which case assign into that array. We don't see that part. That's the assembler. Now it's adding to the, trying to add something to the map. Now, how to explain this? There's a thing, there's a structure in this class called an ASSOC, which means an association. Maybe I can draw a picture of one. Not of an association, but of the main structures in the map. There are, let's just for the argument's sake, there are 17 things called buckets. Okay, so we got 17 buckets. I don't want to draw 17 boxes. And so there are, in order to locate something, you need to know what bucket it's in and what its identifier within that bucket is. Okay, that's how you would find, that's how you would locate an item in this scheme. Okay, now this here hash bucket refers to the bucket, and this here hash value refers to the index within the bucket, I believe. I might have it backwards, but I don't think so. Now the way it works is this. We haven't done anything yet. What this thing is supposed to look for at this point is given a key value. Our key value happens to be 214. Identify, locate these two numbers that correspond with the number 217, right? And then see if there is something called an association that has those two properties that's in bucket, the bucket and hash value identified. Well, nothing will now because we haven't done anything yet. So I'll step in here. Now, this here is the key magic algorithm for computing the two special numbers. Okay. Now I'll step into it because this is a function, and this is just taking a modulo, and this is just the number 17. Pretend this is always 17. Okay, so there are 17 buckets, and so the hash bucket will refer to a number from 0 to 16, which is the bucket number. This value here comes from a special magic function, a secret function, which I'll explain in a minute, which does this magic trick. Okay, that was returned now. It returned the number 13. Okay, it didn't have to return that number, but that algorithm gives us 13 for key. Now hash value percent, that's just going to be the same. Value and bucket, it turns out in this case, came out the same. Now if we don't have a table yet, and we don't, we return no. Okay, now that indicates that we did not find an association for key. Okay, that brings us in here. Furthermore, we don't even have a hash table, so we gotta create one. So we gotta create a thing, our buckets basically. 17 of them. Alright. A couple of assertions. Now it's possible to call this function to reinitialize the hash table, but I never will, but some people might. Alloc now indicates whether or not we want to do the allocation, or do we only want to set this value? So you can see how someone might call this prior to adding anything to the map in order to change the table size without allocating anything. But now we are going to allocate. Now this is an array, and the array is an array of 17 pointers to association structs. For now, just pretend that an association connects a key with a value. Okay, and now we're making 17 pointers to such things. So we have an array of pointers to associations that haven't done anything. I'm just making them, and here they are. Okay. There are this is an array of 17 pointer values. Now, does that count up right here? Well, one pointer value is 4. If it were here, Each line would be four pointers, right? 4, 8, 12, 13, 14, 15, 16, 17. So that makes sense. If starting from here, there are definitely 17 pointer values. Now what we're going to do is, what the thing does is just zero it out initially and set this value, which already was 17, back to 17. Now we're going to create an association. Okay, so now we need to know what these association things are. An association is an internal class defined within this class near the top here. It is a pair, and a pair is a key value pair, right? So this is what goes in square brackets. This is what's on the other side, the right-hand side, left-hand side, right-hand side. So an association is a pair that has a special number called a hash value and also contains a pointer to another association, and the idea is that we can have a linked lists of these associations, and that helps in cleanup. So so where are we? Now we're creating a new one. Now there's something here called free list, and I had trouble sorting this out before, but I think I understand now. This is the list that in the end, it's a linked list that in the end will be used to clean everything up. And it begins with having a value null. This here is just malloc, okay? I showed you before that these plex things are essentially memory blocks that have pointers in them. First, I'm going to just step over this. Okay, now the block, it turns out this block size is 10. 10 associations is how many we're going to create in this block. And the return value will go into here. This is currently null. So remember, an association has a key, a pair, which is a key value and a right-hand side thing, which could be any size. And we're going to make 10 of them. And I run over this, and here it is, P block. It's going to be quite large because our struct is quite large. See, it goes all the way down to here. So it's quite big. I don't know what the size of one is. I'm not tracing it out or anything. Now, recall that a plex is in itself a pointer, and beyond the pointer value of the plex struct, which is what this thing is the data. And this thing points at 90, and here's its pointer value, 0. Okay, it's initialized to 0, and so therefore the data part starts here. So our association is going to be placed here. Well, this is, it's declaring one and saying that this is where it is. I haven't done anything with it. Now, block size, which was 10, is minus, take away 1, is going to be added to this position PSR. And blocks, if you add integer numbers to things that have size in C++, that means 10 assocs worth of distance minus 1 will be added. So following this plus equals, p assoc will be pointing at the 10th element in the array of plexes that we've been given by this. Alright, so it'll be down near the bottom. Now what it does is it loops through backwards. Currently p assoc is pointing here, so it's easier to see here, 90, right here, right? Now that's pretty good because that tells us the size. If there's one that fits in here, then it looks like it's this is 16, 30, 27, 28 bytes. One assoc is 28 bytes. Must be. Yeah, okay. Now an assoc thing has a pointer to a next, right? But it's not at the head of the assoc. If you recall, there's a pair. So there'll be part of this will be a pair, and then there'll be a pointer to next, and then there'll be something called a hash value, which I guess will probably get set to 0. Well, I'm just going to step right over this for loop and run up to here to show you what happened. It's easy, you see it easily when you do that what's been placed here are a bunch of pointers. Alright, we started at 90, and some zeros got put here. Okay. Well, the first one would have had 0 as its next pointer because it's the last one. It's the last one in the list, right? Walking backwards. The last thing in the list points to null, and then this pointer should point. If you read this backwards, should point to the 90 position where the next assoc is. So 1641390, 1641390, that's here. And this one should point to 1641374, that's here. That's the next, and these are all assocs, associations. We'll call them associations. Okay, so what we have is 10 associations in a block, and they're all connected by those next pointers. Now, they don't have any data in them yet, but we can use them. They've been allocated, and we would like to use one of them for our new element. So far, we're just talking about what you would do, simple, not simple, but memory management, allocating memory, right? And making it a linked list so we can free things, and nothing, no magic or anything is going on. Now, of course, there's this free list. Free list is the thing that, in the end, it has got to point to the first element in the chain, so that we can free everything. I think either the first or the last. Well, it's currently pointing at 1641294, which is somewhere in here for some reason. How did that get set equal to that? Is that just random? No, we're creating a new association and setting it equal to what P free list is. Oh, I see. That was the last one that was assigned during this loop. So it should be the penultimate one in the list. We're going backwards. We're going backward. One 164,129. Oh yeah, that's right. 164,129. That's definitely right near the beginning. In fact, I think it's the first one. 1294. That's here. That is not. No. Yes, it is. It's the very first one. It's the head of the block. Okay, that's good to know. So now the new thing that we're creating then, or declaring, is the first association in the array. And what are we going to do with it? Well, I want this to stay here. I want this to stay on A. It's easy because we can see the transition. What this thing would like to do is zero out that association structure, right? But it doesn't want to get rid of the next value, the next pointer. The next pointer are these bytes here, right? So it saves it off, zero out the thing, zero out the association struct, and then replace the next pointer. So we're back. We didn't lose that, and everything else is zeroed out. And so that's all that did. Now it turns out that association is next is also identical to free lists next, because those two are pointing at the first node, turns out. And it's also true that hash value got set to 0. So everything got initialized to 0. Now, what we're doing is advancing free list, okay, to point to its own next pointer. I see, okay. So free list is now going to point here. Maybe free list means the elements that are free, available to use, not to be free, but that are available free memory. This is allocated memory in the sense of someone's using it. Okay, now is that true what I just said? It is pointing at B0, exactly where I said. Our thing has a new member, and now we want to call the constructor for the association with value key. Key is if you remember from like an hour ago, the value 217, I think it was, 14. So that's calling a constructor. I think I pressed H. Okay. Okay, so now the idea of this is called a placement new. We've already allocated the data, but we want the constructor to be called for initialization purposes. So key, this pair segment of the association will get initialized. See? And these things, well, they're already 0, but if they weren't, then it would 0 them out. Now we're returning that, and we now have an association for key whose that points here. It has a next pointer. Where did it go? 90. That's the next. No. Where did it go? This D6 must be 214. I'm sure it is. And the next association should be at D0. Why is it not D0? Well, let's keep going through and see. P assoc next is null, it says. So let's see if that's zeroed out. Oh, I see. So there we were really careful to put it in and save that value. But the only reason we needed to save it was for that other logic that advanced a freedom pointer, and now it's no longer of any use. Okay, now the hash value we computed as 13, so we save that, gets saved as the association's hash value. And now we've got to set a next pointer for our association, and that now brings us back to the buckets. Now I think the buckets, I should have had them in here. Where's the buckets? Here. Here are the buckets. Remember, initially zeroed out. This is a different thing. This is the array of the associative array, and this here is the bucket, the bucket list. I'd like to leave that. Oh my god. Okay. I'd like this to be 90. If it is 98, let it be 98. Okay. Here's the bucket list that has 17 buckets, 17 available places to put pointers to associations in. Okay. Now, normally, we're not in the normal case, we're just starting out. So this is all null. But normally, at all of the positions maybe all the positions in the bucket table, there would be pointers to associations. And what we want to do is take whatever would be the current one in there and replace it with ourselves. But so in this case, there is no current one, it's null. So we're making our next equal to, now our hash bucket is 13, turns out decimal. That's where's well, that's 12 plus 1, isn't it? So that would be 3, 4, 2, no. Oh yeah, no, okay. The 13th, it's not 3, 4, it's the 13th bucket. And we can't see it here. We could turn 13 into hex and multiply by 4 to hex. It's very poor. So starting from 0, 10, 20, 34 is here. So this is where we're going to place ourselves here. But before doing that, we're going to let our next pointer point to the next pointer of the association that might have been sitting there but isn't. So for this first step of nothing, how do I get that to stop changing? And then this next step is going to put a value. Well, just remember it's right above these FDs. 10, 20, 34 again. See? So that's our pointer. And so now the bucket contains one element. Sorry, bucket number 13 contains an element, and that element is the only element. And in fact, each element of the bucket contains a linked list of associations. Okay? So there are 17 linked lists in the bucket list, and the hash bucket tells you from which of those linked lists to search for your item. Now we're just returning the value pointed to by this thing. And making an assignment. Now that thing that returned a reference to my special struct, and we're setting it equal to that value. And that's automatic. And we can't really see it unless we go back to the bucket. This is long, isn't it? But I think it's important to really understand this. Here's the table. Here's our thing, and now we just did an assignment on what is pointed at, what this points to, which is 1641294. Okay. Now, the first thing in this this is an association. First thing is a pair. Remember, the pair is a key value and a value type thing. The key value should be 214, which it is. Or 12. Oh, 6, okay. My memory was right. So that's the key part of the association. And the next thing is a linked list. This here is a pointer to a linked list. Oh, no. It is a linked list. And what's a linked list? What are the elements of a linked list? Like, what does it have for members? What are the members? A lot of functions. Where's the member? Correct. Here's the constructor. Function, here. A node star, and a count. Okay. Node star, and a count. The count value is 2. So it appears though this linked list has 2 elements. And this here is a node star at 1645F18. Okay. Now a node star first has a pointer to a node in it. Or a node object has two pointers, like a next and a prev. Here's the next value, here's the prev value, and then there's a pointer to a list, which is there, and then the object data. The object data in this case ought to be a rect, which has 4 integer values. In this case, 10, in decimal 10, 20, 66, and 1C2, 450. See? So everything is just exactly as expected, and all this thing does is compute those hash numbers, the 2 hash numbers, and add things into the hash table. And when there's a thing in the hash table, it chains to another thing. And so basically you have a list, you have an array of 17 linked lists. And the other block of data with the association things is just memory, okay? That association buffer with the 10 things, that will grow and so on as more things are added. But it's just memory, and there's a little internal memory manager. It turns out that Cplex thing itself is part of a secret special memory manager. I found this out online, of MFCs. MFC has within it, apparently, a highly efficient memory manager, and Cplex is part of it. So I was looking at Cplex online, and I ran into this page, and I'd like to read the article. It's still in here somewhere. Actually, I think I bookmarked it. This might be it. Yeah. Okay. Undocumented NFC class called cfixedAllen. And on page 2 of that article, it breaks it down, and then it mentions Cplex. Where's Cplex? Here, see? Both the remaining unknown is the mysterious Cplex pointer. I will not go into the details of this class, but just know that it is the class that does the actual CRT allocation calls, and it only contains a pointer to another Cplex object. in order to create a linked list of cplex, so its size is only 4 bytes. And then he explains cplex and how it all works. Now, you might be wondering, well, what about this, the hash bit? What about that magic that created the number 13? And actually, I wanted to get to that specifically more than this other stuff, but I'm glad we walked through this first. And I'll leave this here. I'll show you, again, the code that came up with the number 13. MSDN calls this the identity hash. Okay. Now, you may have noticed that the bucket hash, and the other hash were both the same values, were both 13, right? Well, remember that 17 is the number being used as the value, the number of buckets, right? And what does this thing do? Well, it divides numbers by 16. So it's identity in a sense that if you divide all your key numbers by 16, and there are 17 buckets, then I think if you work it out, then that means everything fits nice and evenly into the 17 buckets. You see? Like its bucket value and key value are going to be the same. And so that's a type of identity. But it turns out that it doesn't matter what you do with this thing. And I tried all sorts of experiments. It doesn't matter what this thing returns. As long as it returns values in an even-handed way, your map is going to behave efficiently. You could just omit this, and that's just as good. It runs just as fast for allocating and for looking up, same speed. The speed for adding things to the list increases linearly with the number of items in the list in the map, but you can speed it up by simply adding more buckets. If you had a whole bunch of buckets, the thing is really fast. And there's a balance. There's a best number of buckets probably, and you might want to try to ensure that the number of buckets is sort of the identity thing here should return numbers so that it doesn't have like a remainder, like in the case with the prime thing, where more things are going to end up in one bucket than in another. That really slows things down because every time you hit the bucket that's getting hit a lot, it has to walk through more nodes. Anyway, that's quite a lot, isn't it? I'll leave it there.